calculus on the first fundamental theorem of calculus, part 2, the last problem. I apologize that the sound for some reason cut off on the first part of the video here. So let's pick up right where that one left off so you can hear the explanation of what we're doing on these. So we're given the graph of function g, shown right here. So you can see there's some strange looking piecewise function made of geometric shapes. And then we're asked to find these definite intervals. So again, the key thing to remember is what these represent graphically is the area between the curve and the x-axis. So let's start with the first one that goes from -2 to 2. We'll go back to our graph here. So notice from -2 to 2, we've got this semicircle right here. So area of the semicircle is 1/2 pi r squared. In our case, that would be 1/2 pi times, you can see this would be the center of the circle, goes an entire circle. So you can see the radius is 2 each direction. So it'd be 2 squared. Well, 2 squared is 4 times 1/2 gives you 2. So this is 2 pi. So that's the area between the curve and the x-axis of the semicircle. That's what our definite interval would equal. Notice on the next one, from -6 to 7, we've got a coefficient of 4 right there. And remember, that can be pulled outside the interval. So this would be the same as 4 times the interval from -6 to 7 of our function is g, we're given g of x dx. So whatever we get for our area between -6 and 7, between the curve and the x-axis, that will end up getting multiplied by 4. So this one we've got a bigger interval from -6 all the way to 7. So that's almost, well, not quite the whole graph here, but it starts from -6 right here all the way to 7 right here. So let's first find the area of this triangle right here from -6 to -2. We already know what the area of the semicircle is, so we can go 1/2 the base times the height. In this case, the base, you can see from -6 to 2, that's 1, 2, 3, 4. And the height, you can see goes up to a height of 3 right there. So that's 4 times 3, 12 times 1/2, so the area of this triangle is 6. Then over here, let's draw a vertical line here, because these values are not always at the x-intercepts like they have been so far. So here we've got, to stop right there. So there's a couple ways you can handle this. You can evaluate the area of this whole thing as a trapezoid, notice, because these sides are parallel and the other two sides are not. Or if you want, you can also split it right here. That's what I'm going to do here, split it into the triangle and rectangle. Either way. So since I split it up here, the area of the triangle again will do 1/2 the base times the height. So the base here, you can see from 2 to 5 is 3. So 1/2 times 3. And the height of the triangle, you can see the height is 4. So we get 3 times 4, 12 times 1/2 is 6. However, remember, any regions below the x-axis, when you evaluate the definite interval, they'll end up giving you a negative answer, because essentially all the heights, the y values, are all negative. So the area is still 6, but the definite interval would give you -6. And then we've just got our rectangle here, which would just be base times height, or length times width, however you want to word it. I'll just call it base times height here. So the base here, you can see from 5 to 7 is 2, and the height is 4, gives you 8. But again, it's below the x-axis, so the definite interval would give you a negative answer of -8. So, you can put those all together, 6 plus 2 pi minus 6 minus 8. You can simplify them first, but I'll just kind of write it here so you can see where it's all coming from first. 6 plus 2 pi minus 6 minus 8. So if we simplify that first, you can see the 6's cancel out, and we're just left with 2 pi plus 8. And then if you distribute the 4 into that, to make it a little simpler, that would be 4 times 2 pi, 8 pi, plus, oops, sorry, that was a minus 8 one, not a plus 8. then 4 times negative 8 would be negative 32. So that's what that definite integral would equal. Then the next one is from 9 to 0. Notice the lower and upper limits are in the wrong order. It's supposed to be the 0 here and the 9 there. So whenever that happens, that means when you evaluate it, they'd be substituted in the opposite order, giving you the exact opposite answer. So we can flip it and just realize it's going to make it the opposite of what the integral from 0 to 9 would give us. So just take a close look, keep a close look out for any ones that are in the wrong order, where the larger number is on the lower limit and the smaller number is on the upper limit. Flip it and make it the opposite sign. So now we have to find the area between the curve and the x-axis from 0 to 9. So notice we've got a lot of that already, so we want to start at 0 though. So we've got to split this quarter circle, the semicircle into 2 quarter circles. So we can start at 0 right there. And if the whole semicircle is 2 pi, the quarter circle is going to be half of that, which would just be pi. And then we've got this other triangle, since we have to go all the way to 9 right there. We already know what these two are. So again, for the triangle, 1/2 base times height. The base here, you can see from 7 to 9 would be 2, and the height would be 4. So that gives you 8 times 1/2 is 4. Or the 2 and the 1/2 cancel out, but again, it's below the x-axis, so it's negative. So it'd be pi minus 6 minus 8 minus 4. And we've got a negative on the outside. But again, we can simplify it within the parentheses first. So that would be negative 14 minus 4, negative 18. But then when you distribute the negative, you would get negative pi plus 18. So that's what the definite integral from 9 to 0 would be. All right, and the last one dealing with this graph goes from negative 2 to 5, but it's g of x plus x. So remember, with integrals, just like with derivatives, you can integrate them separately if they're added and subtracted. And here, in order to figure it out, we actually have to split it. Sometimes it's useful to split into 2 separate integrals. So the first one will be negative 2 to 5 of g of x. And then plus, the next integral will be from negative 2 to 5 again, but now of just x. So we evaluate the first integral using the graph, like we have the first 3. But the second integral, we're just going to integrate like a normal equation. We can just integrate x. That's why we needed to split into 2. Because one, we're using the equation, x. The other, we're using the graph. Because we have the graph of g of x, but not its equation. So from negative 2 to 5, let's see if we've got that already. Negative 2, starting right here, all the way to 5. Yeah, we do have that. So that would be 2 pi, because it would be the entire semicircle, minus 6. So this part is 2 pi minus 6. And then, usually when they have ones like this, that's not going to be super complicated integral, and it's not here. You can see just using the power, this is x to the first, so it would become x squared, add 1 to the exponent, then divide by that exponent. The plus sign is still right there. And then, remember, the official way to write it is with just one vertical line like this, from negative 2 to 5. But again, I adapted that just to make it a little more user-friendly there. And you can just turn it into brackets like that. So it's a little easier to see that we're only substituting these into the x squared over 2. So if we keep evaluating that, 5 squared over 2, that's 25 over 2, minus negative 2 squared is 4 over 2, gives you 21 over 2. Is what that one integrates to be. And then we've got a negative 6, which you can make it over 2 as negative 12 over 2. So that we can combine it with the positive 21 over 2, so 21 over 2 minus 2 gives you 9 over 2. So our final answer for this one will be 2 pi plus 9 over 2. And that concludes the notes for AP Calculus on the topic of the first fundamental theorem of calculus. And here we just finished up that last problem.